Welcome to the Behavior Speak podcast. Now, here's your host, Ben Ryman.
All right, welcome to another episode of the Behavior Speak podcast. I'm really excited today to have Marc Lanovaz from Montreal with us today. Marc is a researcher professor at U de Montréal, and he's doing some really interesting research right now as it pertains to artificial intelligence and machine learning in combination with behavior analysis. Really cool stuff, really kind of forward-thinking stuff. And so I'm really looking forward to kind of diving into this. I've been reading a few of his papers, and I really see a lot of potential for this sort of years down the road to really change the game for kind of how we're doing our work. So really excited to have you with us today, Marc. Thanks for being on.
Well, thank you for the invitation. I'm really glad to be here too.
Super awesome. I just heard Marc speaking at Aunt Abba in December of 2020, and he did an incredible presentation on AI, which got me really excited. So I was really pumped to bring him on. So maybe we'll get right into it, Marc, and then you can give us maybe just a little bit of your origin story, kind of tell us kind of how you got into the field of ABA, and then kind of what kind of work you're doing now, and kind of how you got into AI and machine learning, like what brought you there.
Well, that's a long story. Hopefully, we have time.
We do.
I mean, it's quite a funny story on why I'm in ABA. I was actually a student in an elementary school education, so I was studying to becoming a teacher. So during the summer, I used to work in day camps, and it's the absolutely best job. If they would pay me the same thing to work at the university at day camp as they do at the university, I'd still work in day camps. I absolutely loved it. And then at the end of day camp, at the end of summer, I was looking for a job. So my salary at day camp at this time was $7 an hour. And I was looking for a job to work with kids. And there were some kids with disability in our day camp. So I was able to be exposed to that. And the highest paying job that I could find was to work as an early intensive behavioral intervention therapist. So I found this job, which they were looking for just therapists, and they were providing all the training. It was some of the first individuals in Quebec to receive this type of therapy. So so they were paying me, I think it was $14 an hour, or $12 an hour. So they almost doubled my salary. So I was really excited about it.
Wow. Awesome.
So it's a really silly story because it was really just based on, I was looking for a good paying job to get through university. And I started doing it, and I already had a strong science background, and I absolutely loved it. So once I started, I knew that I wanted to do a master's degree in ABA afterwards, and there was no one certified in Quebec at the time. So I had to, so once I finished, I decided to do my master's degree in ABA from St. Cloud State University. And I had to do, at the time, they called it mentorship instead of a supervised experience. And I had to drive once a month down to Plattsburgh State University to get supervision because there was nothing else around, and the online was not as well developed as it was. And I met this amazing professor, Patricia Egan, which actually provided supervision to me for free. So I was really, really lucky. Actually, at the time, they called it mentorship. So she provided mentorship to me. So I did my master's degree, and I studied with John Rapp at St. Cloud, and he really encouraged me to continue at the Ph.D. level. So I said, why not? I like doing research. So I went to McGill University because we don't have any behavior analysis programs here. I did it in educational psychology, but with a behavior analytic, from a behavior analytics standpoint. And I really enjoy it. And then I never stopped from there. I was hired as a professor at the University of Montreal. And I got interested in technology because I was realizing that a lot of the we have very good interventions in applied behavior analysis, but they're often challenging to implement. So I want to use technology to implement some of these behavioral interventions. So we developed an app called the iStim, we wish to support parents in reducing engagement in stereotypy. And following that, I really realized that that's what I wanted to do, to mix behavior analysis and technology. So I had a sabbatical a couple of years ago, I think it's about 3 years ago. And I decided to go back to school. So during my sabbatical, I went to do graduate coursework in software engineering because I wanted to learn how to program a bit on my own, because I'm very dependent to individuals who program, and I wanted to reduce a bit of that reliance. And probably most of the listeners or the audience is aware, but Montreal is actually a hub for artificial intelligence research. So I decided, what the hell, I'll take some programming courses, but also take some artificial intelligence courses. And it really blew my mind on what you could do with these types of algorithms. And I decided from that point on that that's what I wanted to do in the next few years, is to apply the machine learning and artificial intelligence in general to improve the delivery of behavior analytics services. So that's really, it's a long story where I started from a guy who just wanted to be a teacher, and ended up doing some programming and artificial intelligence work.
That's amazing. Yeah. It's interesting to say that. There's actually a researcher out here in BC, Dr. Vicky Knight, who is sort of combining your early love of day camps with coding, and she's doing coding day camps for kids with autism. So I thought that might be might have been a direction you could have ended up if the pay was really good at the old day camp.
Yeah. Yes, absolutely. I mean, I think that it's really nice, and I feel that in general, as a side note, we should be training kids to code earlier, because the things you can do, even not with machine learning, when you know how to code, you are so much more efficient with so many daily tasks.
100%. And from what I've seen, it seems like there are quite a few folks kind of with autism that are involved in sort of the computer sector doing coding and those sorts of things. And so, that certainly meshes well. So AI, machine learning, these are really big terms. I mean, for me, all I have is kind of the movies to go on, and things like, what was it, 2001, 2010, those different movies where things are taking over the world, and machines are coming and taking us all down, and eventually we get to the Matrix where the whole world is taken over by machines, and so it becomes quite scary. But it sounds like a lot of that is just the movies talking. Maybe you could just give us kind of a general overview in kind of layman's terms on what is artificial intelligence and what is machine learning, and how they relate.
So there are many different definitions of artificial intelligence, but I'll use the one that I like the most, which is basically the study of how to make computers do things at which, at the moment, people are better. So basically, artificial intelligence in the 1940s and 50s did not mean the same thing as artificial intelligence in 2020. Artificial intelligence in the 40s and 50s might have been to do complex computations, to solve some statistical problems, for example. So doing some types of simulations, which computers were becoming better than human beings. So they were becoming better at calculating logarithms, that they were getting better at doing multiplications, doing computations in general. Whereas nowadays, I don't know anybody who would look at a calculator, like your handheld calculator with a solar powered, who would say that that's artificially intelligent.
Ah, gotcha.
Nowadays, it evolves. So now artificial intelligence is what we want to study, how to make computer do things at which at the moment people are better. So one of these things was, for example, labeling images. So that was one of the challenges which they really, really improve in. When you hear a lot about the artificial intelligence research, it's a lot about what they've been doing with image recognition and speech recognition in the past decade in particular. Because in the year 2000, between 2010, probably that machines were not any better than us at image detection and at speech detection. In 2020, it's still artificial intelligence, but maybe in 2030, it's just going to be the new normal, and it won't be artificial intelligence anymore. So that's what I like about it gives a science-based and an evolving definition to artificial intelligence. Now, from a behavior analytics standpoint, there are just a ton of things that we do as behavior analysts that we are better than computers. So it's a whole new area of study that people can open, because behavior analysts are better than machines at doing most of the tasks that they do on a daily basis.
Sure.
So this is really where we push. Now, machine learning is a branch of artificial intelligence, or a subset, or tools maybe used by artificial intelligence. And how I like to describe it in simple terms, it's basically a series of computer instructions, which we call algorithms. Algorithms are just a series of computer's instructions to do something, designed to detect and predict patterns in data. So basically, you give data to these machine learning algorithms, and what they do is they find patterns, or they predict patterns, or they learn to predict patterns. Now, there's this whole issue. Some people will argue that machines can't learn. I think it's more semantic more than anything else. I think that, if you're taking on new data and then improving over time, I don't have any issues with calling it learning. But obviously, not everybody agrees with this conceptualizations of machine. But really, it's so machines are really these types of algorithms, and there's three main types of machine learning. There's unsupervised learning. So unsupervised learning, you provide a bunch of data to your machine, and then it will find patterns by itself. So it basically, you give the input data, and I'll use these words a lot today probably, but it's a lot about input and output. Think about it about behavior. To me, the input is the discriminative stimulus that we provide to the child, and the output is the behavior. So it's a bit the same thing with machine learning. You give it discriminative stimuli, so to differentiate between different conditions. It can be pixels, it can be sound waves transformed into numbers, it can be actual numbers or percentages. So that's the input that you're giving it, and it gives you an output. And in unsupervised learning, it just tries to categorize the data as it seems to provide the best fit. Whereas in supervised learning, which is what I think we'll mostly talk about today, and that's what we've been doing a lot of research in, is we actually tell the machine, a bit like in discrete trial instruction, we give it the output too. So we give the machine the input, so the discriminative stimuli, and we give it the correct responses, so the output. And then by repeated trials, so by doing different types of things, depending on the algorithm that you're using, it learns to predict the output. And the ultimate test in machine learning is exactly like in behavior analysis. And there's a lot of analogies to be made here, but it's exactly like behavior analysis, because what we're trying to do to the machine, and the ultimate test is whether they're able to predict or detect the pattern in untrained samples, untrained exemplars. So when we report results in research studies, we always report how the machine is doing on untrained samples or untrained data. So in that case, when we test it, we no longer give it the output, we train it using the output in supervised learning. But once we want to test it, we give it new data with no output, and then we ask it to predict what the output is. I don't know if that's clear.
It is. It sounds, and you're right. There are a lot of parallels here to sort of behavior analysis. It sounds a lot like shaping.
Exactly it.
shaping and generalization.
Yep. Some of these algorithms work very similarly to shaping, actually. I mean, the algorithm gets feedback based on its responding, and then it must adjust its responding based on the feedback. But the difference, or not a difference, but an issue that we have to be very careful with many of the algorithms, and maybe we'll get to it a bit later too, but is, we could probably learn a computer to predict most of the things almost perfectly or at a very high level of accuracy. But if you do that with a data set, it won't generalize. Or it may generalize, but it won't generalize as well because it will fit the data too closely. A little bit, I like the example of, you're teaching the concept of cat to a child with a developmental disability, and all you do is teach him or her white cats. So when they see a black cat, they might not recognize it.
Of course, yeah.
So that's why you want to train it a bit more, if I can use a behavior analytic term, train loosely, a bit more loosely.
Yes. Yeah, no, that makes a lot of sense. Okay, that's interesting. Okay, so we've got AI, which is essentially the term. So it sounds like with AI, if I was understanding your explanation, AI is sort of the term we apply when this stuff is kind of new, and as we kind of start using it more and more and more, then it just becomes another technology. And so, like you said, calculators and computers and, the VIC-20 and the C64 aren't AI anymore. They're just computers, but they were AI back in the day.
That's exactly it. Yes.
Because it was new. And so now we're doing AI in like one of your studies, which we'll be touching on pretty soon here. You're using AI with functional behavior assessment. Eventually, hopefully maybe one day it'll just be, remember in the old days when we did functional analysis without technology? And it'll just be functional analysis. It'll just be the way of doing functional analysis, and AI will be for some other new thing.
Yes, absolutely. It's an evolving definition, because probably to the very least at this point, machines are very, very far from performing as well as human beings. So we'll be pushing the boundaries of AIs for decades and decades and decades. I mean, people sometimes have the impression that, it's going to replace us all in 10 years. That's really, really far from reality.
Well, and I think also because I've heard that before, the idea of sort of AI taking over. We see this sort of with things like the self-check at the grocery store, and that's replacing the cashier sort of in the line, and that being a problem. But it does create new kinds of jobs for people to build self-check terminals and that sort of thing. And so I think we'll probably see over time with AI, it might maybe replace certain tasks, but it will create new roles and new jobs and new careers. So
yes, I like to compare it to your librarian. Most people thought that, with everything indexed nowadays on the internet, you wouldn't need a university librarian. I can tell you that it's quite the opposite. There's so much information out there that we need well-trained librarians to support us in what we do. So I think it transforms what we're doing. And it is a challenge, obviously, for individuals who do not have as much lower education, which we can see in the job market. But it creates new opportunities. But supports need to be put in place to prepare the future workforce. Let's put it that way.
So maybe let's we could start diving into one of the studies that you put out recently. I really found this study that you did in collaboration with a few other folks on machine learning to supplement behavior assessment. I think this would be really interesting to listeners. So maybe you could talk a little bit about that study and kind of how it came about and what you found. If you're collecting continuing education credits for this episode, you'll need to know the 3 secret words. The first secret word is machine.
Well, first of all, how it came about, I do not know, because I was added more towards the end. So I was added as a collaborator at the end. So I have to give nearly all credit to Jordan Bailey and his team. I think he was at Western Michigan doing his Ph.D. So basically, how I got involved is he contacted me to get more QABS, because he had used some QABS from one of the studies I published several years ago. And then I had been on a reviewer on an earlier version of the paper. So I told him, hey, I was a reviewer. This is really cool. I really love your study. I don't have any QABS, but I have formal training in these algorithms. And if you need support to do it, to push it further and to see what you could do, it will be a pleasure to get involved. But it's really up to you. And he said, oh, sure. So we started to work together, basically. So we improved on the algorithm he was already using. And we really made a few tweaks to really make sure we're using best practices in the use of these types of algorithms, because it's a lot easier when you have formal training, obviously. It's probably one of the best decisions I've ever made to go back to school, because you can learn it from the internet.
Sure.
But when you have like world-class professors who teach you, the advantages and disadvantages and how to do the math underlying it, it really helps. So basically what Jordan did is he extracted 49 QABS from the literature, where he had all the data from the QABS, as well as functional analyses that were done following the QABF or before. It didn't really just matter. But he had both the data sets. So that was a perfect opportunity to test for machine learning, because you have the input, which is the results of the QABF, and you have the true values, which is the result of the functional analysis. So you have basically your input, in this case, is the QABF data. Your output, or your correct responses, is what function it is. So what he found is if he applied the rules from the QABF, so when you buy the QABF or you purchase it, you get an article that goes with it that tells you how to interpret it. Well, when you had multiple functions, it would only identify all functions correctly about 50% of the time if you use these rules. So Jordan asked himself, maybe you could use machine learning to develop better ways to take that input data and to obtain a more accurate function. So he started by using more traditional machine learning algorithms. I call them more traditional because what you're hearing a lot in the media lately when they're talking about deep learning and the images, they often refer to deep learning networks. Now, these deep learning networks, we'll probably talk about them a bit later, but they're really cool. They're really powerful. But when you don't have a lot of data, they're not as effective. And sometimes traditional machine learning, which was developed a bit earlier, or at least used more a bit earlier because they don't require as much computing power, were more of the norm. So he started by testing these algorithms. And what he found is that, by using some of these typical machine learning algorithms, he could get agreement about identify all the functions in about 65% of cases. So an approximately 15% to 20% improvement if I don't round. Okay. So it's still a huge improvement, but it identified the correct function 65% of the time doesn't sound too exciting. And I'm pretty sure you agree.
Yeah, for sure.
So Jordan said we should really wanted to do the deep learning, so the artificial neural networks, but we didn't have enough data because we only had 49 samples. So what we did is we did something called data augmentation. And that's where I came in and I could provide support. I provided most of my support. Is that data augmentation is the equivalent if you're training a computer to recognize a cat, okay? And you only have 30 images of cat, okay? It's not a lot to train.
Right.
Well, what can you do? You can flip it. You can blur it a little bit.
Mm-hmm.
You can zoom in. So with one image, you can create many more that still remain a cat, despite the modifications to it. So even though you have a single image, you can create new images that are still cats and that promote generalization, because that's always the issue. You want your model to generalize to untrained exemplars. So what we did is that we generated new QABS based on the original ones by just playing around with basically the QABS you have when you collapse the data at the end. You have basically 5 scales, and we use only 4 because one of them is for physical problems and there weren't enough in the literature. So there's one scale for attention, one scale for tangible, one scale for automatic or non-social, and one scale for escape. And you have, for each of these, you have a gravity score, which can be a score from 0 to 5. And then you can have, that's an endorsement score. That's 0 to 5. And then you have a severity score that each of these value can be 0, 1, 2, or 3. So it can go from 0 to 15. So you have a severity score that goes from 0 to 15 and an endorsement score that goes from 0 to 5. So what we did is we said, well, parents usually fill up these questionnaires, or staff. They're not perfect. They probably often hesitate between selecting an item or not. So we just decided, well, we'll create 10, I think it was 10,000. Here, I can even check. I have it in front of me. But we created many. I'll say that. Mm-hmm. I just have a total blank from these 44 samples.
It says an experiment too. You augmented the data with 1,000 artificial samples.
Thank you. You're better than me at finding my own stuff in my. It's because it's not written in numbers. So we generated 1,000 samples basically.
Right.
So and then we trained an artificial neural network to identify patterns in behavior, and we were very careful to make sure that it was still generalizing. So there was when we were training these models, we made sure that the ones from which they were derived were not including in our test data set. Because if not, it wouldn't be show generalization. It would be just showing that I'm good at generating similar data sets.
Right.
So to avoid that, we had to remove it. And surprisingly, and I say surprisingly because I would have never believed you if you would have told me beforehand that he could achieve an accuracy of 88% on multi-label functions. So that's multi-label accuracy. What that means is that it not only identified single functions, it could adequately identify when a child had or an individual had a behavior with multiple function, which is very, very difficult to do, even with functional analysis.
Mm-hmm.
So I was really, really impressed that he could push it up from the initial about 50% to 88% just by generating new data sets that were similar and then training it on a neural network, which is a neural network is basically a type of machine learning algorithm.
Well, that was going to be my next question. What is this artificial neural network?
People think it's a bit like the brain.
Yeah.
I'm not sure I agree with that definition. I feel it's just a way, because it's structured like it looks like neurons and synapses where you have connections between different points at different areas. So that's why they call it. But it's really not clear, and it's really not, to my knowledge, it's really not proven either that they function like brains. It's just because it looks like neurons and synapses with the connections.
I see.
So they call them artificial neural networks. So I sometimes, I talked of these topics with some behavior analysts, and sometimes I see some of them cringe when they hear the word, neural networks, like if we were working on the brain. And to me, it's really not the same thing.
We're not talking Star Trek and androids here.
No, no, not at all. I mean, and it's really, it's just math. It really is. It's just multiplying our inputs by different values so that it gets to an output that we want. In simple terms, that's about what it does. And same thing with the word intelligence. Sometimes behavior analysts will shy away from the term intelligence. But it's not this. We're not talking about artificial intelligence. It's not like intelligence IQ. It has nothing to do, or very little to do, with it.
So, I mean, it sounds cool. So, when you created those 1,000 artificial samples that you put in earlier, you were talking about, in terms of the sort of the supervised learning, that you would put in the inputs of the QABF results. And then the outputs, which are those also called labels? Did I read that correctly?
Yeah, the outputs are called labels and the inputs are called features. So when we work with these models, we provide them features and we provide them with labels when we do supervised learning.
Right. And so you put the features in, you have the outputs of the labels, which are your matching kind of functional analysis results. In terms of the artificial neural network, you're now putting in 1,000 artificial QABF results, essentially.
Yep.
But you don't have the labels.
Well,
right?
We provide the same label from which it was initially derived, because we would expect a parent or a staff, to make one less endorsement just because they're more tired. There's errors of measurements on all tools.
Oh,
you won't respond the same.
See.
So we just changed one item, which changed two numbers in our matrix, basically.
I see.
So it changed 2 out of the 8 numbers, a bit like if you had an error of measurement. But technically, with an error of measurement, you should still have the same real function.
Okay.
So it made the data a bit more. I really like the analogy. It's like if I was blurring the image a little bit.
Yeah, no, that's really good.
Of the cat. So, and this is in my opinion, this is a good way to go about, because it's true. If you imagine a parent or a staff responding to a QBAF, you would expect them to make some errors in it. They're not perfect, and there's some subjectivities into the items, and that's what we took advantage of to create our 1,000 data sets.
So that 1,000 artificial samples are still using the original 49 functional analysis results as labels, because they're just sort of tweaked. They're just sort of the original ones that were tweaked in different ways. I see.
That's it. The only thing is that we, like I say, if we want to test a sample so that we don't give the label but just the input, we wouldn't use that data to create others, because they would be too close, and they would be, in my opinion, it would mess up the validity. It's the best picture I could take. It would cause probably overfitting and generalization issues. So we don't want that.
So 88% sounds pretty good. I don't know that there's any sort of indirect assessment out there that would have, that high of a number. Is that something then that folks could use now?
I would say not right now. And the issue is simple, as I'm a strong, strong proponent of replication. So, I mean, we use 49 sample. We use something called leave one out methodology,
Right.
which basically we trained 49 different models.
Mm-hmm.
And each time we left one sample out to test. So for a generalization.
Yep.
So I would be a lot more comfortable if it were replicated within another study with other data sets beforehand. Because you never know, you could have these, and I'm not saying our results are not good. I'm just I believe in the scientific method.
Yeah, absolutely.
And I believe that we need to emphasize replication.
So this is a kind of proof of concept, I guess.
Yeah, that's exactly it. That's how I would call it. It shows that it can be done.
Yeah. Yeah.
Is it always going to be 88? I don't know.
Yeah.
It would be cool to test with other samples. There are some things working for us. They came from several different studies, the QABS.
Yeah.
So the researchers probably had different biases when they were conducting the functional analyses and when they were administering them with different populations. So that's encouraging. But it still remains trained on a single 49 sample with what we call leave one out methodology. So the ideal would be if somebody else was sitting on like 100 QABFs and did the same thing. That would be a lot better because we are really on the lower limit of what we can do with machine learning with 49 samples. We may talk about a tutorial we wrote with about 25 samples later, but I mean, that's really, 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 even the 50 is not high. 25 isn't great either because you have a bigger risk of not generalizing.
And you were essentially just drawing on, what was it, like four studies or something? Or there wasn't that many?
I think that was it. I think it was 4 studies.
Yeah.
Don't quote me on this.
Yeah, no.
Go read the article for those who are listening. But I mean, it's about that. I don't think it's much. If it's not, it's probably plus or minus 1 would probably be my best guess.
We almost need someone to replicate, starting with a study that has a whole lot more QABFs. And then experiment 2 is, let's try this all again.
That's it. The problem and the big issue and the big challenge is that you also have to have the functional analysis to go with them.
Right, 100%.
So that is really the big challenge. I mean, there would be other ways to do it. You could do, and I'm just thinking out loud right now, but you could do unsupervised learning on QABFs to see how it categorizes the different patterns. There's many things that you could still...
Well, and the functional analysis takes a while, right? So it would be interesting to sort of, combine that with some of this practical functional assessment that Greg Hanley's doing, where he's only doing sort of 2 conditions, and it's quite a quick FA. He does the FA in sort of a span of 15 or 20 minutes, and so that would be interesting to sort of combine, the QABF with the way he's doing things.
Another thing that could be done is doing natural language processing on the actual interview that the procedures developed by Hanley has been doing. So you could take like all the responses and then do natural language processing and then see if you're able to predict the function based on the sequence of wording that are in the questionnaire. So that could be another way to test it.
And I just see so much potential here. Like if this were to be replicated, multiple times, and we could, reliably get our percentage up in, maybe in the 90s or something, on a repeated basis, and again, I am a Star Trek fan, so some of this sort of future thinking does kind of get into my brain a bit, and I'm sort of picturing, 25 years from now, people going around. Are you a fan of Star Trek at all? Will you know what I'm talking about if I start?
I know what you're talking about. Okay. I'm not a huge fan, but I know what you're talking about.
The classic device in Star Trek is the tricorder, right? Which is sort of this, amazing device that scans for everything, everywhere, all the time, and you can assess anything all the time. And in fact, it sounds on a tangent, folks are actually building those things now. But I'm imagining someone with a little device with a funky 1960s sound and going up to a child and going, the function is, from based on using all this kind of data, and it kind of got me thinking about sort of the right to effective treatment with Van Houten et al. And the least restrictive kind of most effective interventions. And it would seem like it would almost make the functional analysis process in and of itself seem intrusive if you could do this all without sort of having to sort of engage the individual so much and evoke problem behavior and so on and so forth. And instead you just have an algorithm that can sort of figure out what the problem is behavior is based on a few inputs.
Yeah, that would be really cool. Obviously, we're very far from that. But I would absolutely love to see that. And that may segue into another thing that we're trying to do with artificial intelligence,
Yes.
if you allow me.
Please.
Which is we're trying to automate the measurement of behavior. So we conducted another recent study, which was published in GAB, so in the Journal of Experimental Analysis of Behavior, because it's not quite ready for applied work yet, where we actually tried to use neural networks, so the same type of neural networks we were discussing, or not exactly the same, but similar, to recognize vocal stereotypy in audio recordings.
Oh, okay.
So that eventually, instead of having to pay someone to sit there to record vocal stereotypy, because as you probably are aware, I've conducted a lot of research on vocal stereotypy. And to remain polite, it's a real pain. I won't say pain in what, but it's a real pain to collect this type of data, especially if you want continuous data. So if you're using like discontinuous recording, it's not as bad. But when you're trying to get continuous recording,
right,
it can be a real challenge to measure.
Absolutely, yeah.
So what we did is we extracted 1,500 minutes of audio recordings of children engaging in stereotypy.
Wow.
And during these sessions, sometimes there was treatments in the form of music. Sometimes there was DRO. So there was definitely background sound on these audio recording. And we tried to pick out the vocal stereotypy and then examine if we had the machine measure the vocal stereotypy in one session, what would be the correlation between the different sessions. So technically you want your algorithm, if it's low, recorded by you don't want them to match perfectly. That's not the end of the world. Just think about discontinuous methods. I mean, PIR partial interval recording will rarely match, like a frequency measure.
Right.
But the important thing is that the patterns remain the same. So that's why we use correlations, because correlations will tell you whether the patterns will remain the same or not across different sessions. And what we found were surprisingly high correlations.
Wow.
So we trained it with 8 participants and for 1,500 minutes. So they were not high quality recording. They had nothing special about them. They were just taking off a video. So actually they were even low quality recordings, if you want my opinion. Because if they had a mic close to their mouth, a microphone close, it would be a lot easier to do
than
to do it with a video camera, because the power of the sound that comes out of their mouth would be higher. But basically, we found for many of the participants, so for about 6 of 8, we found correlations that were similar to correlations between discontinuous and continuous methods.
Oh, wow.
So the goal of all that, I came into the topic because we talked about functional analysis, how complicated it is, but it's complicated to monitor the effects of treatments too. We asked parents to collect data, and you and I were discussing it before the interview. It's a real challenge for parents and teachers to collect reliable data.
Sure.
So if you really want reliable data, you have to pay an extra staff just to be there and collect data almost. I mean, it's really, really, really challenging to get valid and really reliable data for long periods of time. And that's an issue too with low frequency behavior. You can't observe 10 hours a day if the behavior occurs only 4. I can't send a research assistant there.
Yeah, exactly.
Or a therapist like for 10 hours just to record a behavior during baseline. So the whole goal of this is eventually to be able to film the kids, then put them into a program, and then it tells you, well, he was doing vocal stereotypy 10% of the time, he was hitting 15%, he hit 15 times, and he bit 5 times without needing to record the data at the same time. And that is really right now what artificial intelligence is all about, when we're saying, teaching computers to do things that humans are better at this time.
Right.
And the technology is right about there. So we have the algorithms probably to do it. what we need now is the data.
Mm-hmm.
Because you need a lot of data to train these
Right,
things.
right. And that data must be out there somewhere. I mean, some of that. I mean, there's a lot of studies with a lot of data. No, or
I don't know. I mean, probably I always say that I'd love to pair up with a big agency in the United States, that service hundreds or thousands of children with
yes,
ASD or with intellectual disability, because they probably have a ton of data. The big job and the expensive job is to label it. Because I can write most of the code, but I need quality data. So, for example, my 1,500 minutes of vocal stereotypy, because we wanted them to be recorded second by second and to have a good ground truth or a good calibration, it took her 3,000 minutes to record.
Oh my gosh! So she had to code all that data.
Yes, you have to label it.
Right.
So that's the big issue, is that you need a lot of data and you need to label it. So that's why we're starting with stereotypy, because they're very high frequency behavior.
Right.
So it's easier to detect the pattern from the noise when you have a lot of data than when let's say I would try to measure hitting. Well, hitting doesn't occur that often,
right,
in most cases. So it would be extremely difficult, to measure. In my example, we recorded second by second. So I don't have the exact number, but we had about 100,000 seconds, to give you an idea. Okay?
Oh my goodness. So she was essentially coding kind of 1 second partial interval recording. Is that sort of how it would have worked?
Yep, that's exactly it.
Wow.
So in total, she had to score 99,000 seconds.
Oh my goodness.
And in these seconds, and I'll say a number, I'm not sure if exactly, let's say 20 or 30% of these seconds had vocal stereotypy in it.
Yeah.
And that's another issue with using behavior analysis. And I'd like to talk about issues because I'm sure people are going to listen, and I want people to find solutions to these problems.
Mm-hmm.
But a problem we will run into behavior analysis is that our treatment are very effective. So what happens then is that you get unbalanced data sets. So let's say I want to test whether a child will respond correctly or will respond positively, so significant behavior change, following non-contingent reinforcement or a time-based schedule, if you prefer. While for vocal stereotypy, our experience has been that if I put music on, I'll succeed in about 80% of cases. Okay? Just a number, an approximation.
Yeah.
But if I have 100 examples, that means I have 80 in which the treatment has worked and 20 in which the treatment has not worked. Well, that 20 is not big enough to do my training, or it's not big enough. I would try anyways, but it's not an optimal level.
Mm-hmm.
It would be better to train my models if I had 50 works, 50 doesn't work.
Gotcha.
Or at least have more that don't work. So that's a challenge. I've been trying to do some follow-up studies, and a challenge is finding these cases that don't work.
Yes.
Because we want to add them to our data to get exemplars.
Mm-hmm.
It's a bit like if you were teaching the difference between cat and dog, but you have a ton of examples of what a cat is, but very few of what a dog is. So now I have a ton of example of which type of child with whom this treatment should work, but I don't have that much exemplars with whom it should not work.
And of course, a lot of our research that we publish doesn't include the stuff that doesn't work. The second secret word is artificial.
Absolutely. I mean, there's quite a few studies that show that there's bias in single case research. So a bias towards effective treatment. And I mean, I was, and I'm not surprised. I mean, it's a challenge to get stuff that doesn't work published. So by going through thesis and dissertation, we've been able to address part of these issues for other studies.
Sure.
But even then, I mean, the effectiveness is quite high.
Well, I know you might have to tap into, I don't know if you've heard the name, but there's a fellow down the States, Dr. Shane Spiker, and he's putting together a journal that will publish failed studies. And so maybe that might be a resource, because he might have some data that of interventions that didn't work and that weren't successful. Yeah, and so maybe he's one, if he's listening. Shane, if you're out there, if you're listening, maybe you can pass some data on to Dr. Lanovaz. Yeah, so much going on here. One piece that I saw, one kind of line I saw in one of the studies was sort of comparing machine learning to statistical analysis and saying that with machine learning, as you've been explaining so well, focuses on prediction and stats focus on inference. Is one better than the other?
They're not designed to respond to the same questions, I think.
Mm.
Because to me, when you're doing stats, you're really trying to see if there's a difference. Or a lot of the null hypothesis testings that's been going on is seeing whether there's a difference or not in treatment. And even in behavior analysis, even though we say we don't do null hypothesis testing, I mean, when you're basically checking whether there's an effect or not, so whether it's true or not. So somewhere you're trying to see whether there's a difference. With machine learning, you're not trying to look at the difference. You're trying to train algorithms to predict what the response should be. So it's very applicable to clinical work because you're often trying to predict. In behavior analysis, I'm trying to predict or measure what the behavior is. So basically, I use the word predict a lot, but oftentimes you can use the word to measure. So I'd like to measure whether before doing it, whether this treatment will work with this child or not. So I would like to know beforehand whether it works or not. I would like to know beforehand. So I'm not looking at differences. I'm trying really to predict whether develop tools that will predict. And then obviously there's still some testing. I want to see whether my predictions with the computer are any better than those done with the gold standard or with a human. So that you will come more to traditional statistics when you come to that testing, because you've shown your predictions, and you can you can usually compute a confidence interval on that prediction. Well, then you can compare it to the actual label. So that's how machine learning can be used. So I think that they're different tools to respond to different questions. And even if we tend to critique null hypotheses testing, there are still some problems that are best answered using that type of approach.
Gotcha. Kind of going back to your just a question I meant to ask around the stereotypy study there. So something I think maybe a lot of folks like myself sort of assumed with AI and machine learning AI is that the AI was actually as if the AI is a thing, and I know the AI is not a thing, but the algorithms are actually aren't actually counting the stereotypy. They're predicting the stereotypy, right? So
they're predicting it for every second.
Right.
So basically we have programs that transform sounds into numbers.
Right.
A bit like, pixels for an image. You can have different colored pixels.
Yeah.
So it transformed that to numbers, and then it takes the numbers and it tries to predict with these numbers whether there was a vocal stereotypy at that second or not.
I mean, you've got the accuracy, so it gives you that percentage piece, but it's not actually telling us how many instances in 1 second or in 10 seconds of vocal stereotypy it was. It's predicting how many there are. I think that's a important distinction, because I think
it's doing like PIR. It's really doing like PIR. So it's not counting them. It's just saying whether the algorithm we developed, but there's so many ways to do it. And what we found is that it was better at a molar level than at a molecular level. That is, if you look second by second, it's not that great, because sometimes a second will finish, another will start, there's a sound in between. But if you average it over the entire session, that's when it becomes a lot more accurate.
Okay.
And there would be other ways to approach the problem. We could have, for example, given the algorithm all the data for a session and the percentage for that session. So instead of doing PIR, I just give it the whole data and the percentage, and then it tries to give me the percentage for that for that whole session. So that would be a way to do it.
Right.
So we could have done it, for example, minute-based. So we're just scratching. What I'm trying to say, we're just scratching the surface right now.
Yeah.
I don't think that the approach we're using right now will be the approach that people will be using when it's really effective in 10 years from now.
I got you.
It's really, we're just showing that it is doable, that you can do it, but we're using basically, it's a bit like if we're using all the default parameters to test this.
Mm-hmm.
We're not pushing it that far. We're just saying, well, listen, we use the default tools, but there are so many different ways that we could approach the problem to solve it. But I mean, the easiest way to start is to start with the default.
So it's really early days for this kind of research.
That's it, because I mean, especially the sound. I mean, we made so many decisions that could have been taken differently. The two examples are classic ones. We were looking at every second.
Mm-hmm.
Well, maybe with certain. I think in each second there was I think it was how many time steps? So there was 10 time steps per second. But we could have used 25 time steps. We could have used a different algorithm. So when you have sounds, there's something called a spectrogram that you can actually see when you're doing a recording on Audacity,
right? Yes.
which is a program. Well, you could actually, instead of feeding it numbers, you could feed it the picture of a spectrogram for each second, and then use a certain type of network. So that has already been done for vocal stereotypy.
Oh, interesting.
It didn't apply well to the type of problem we're trying to solve in our study, but it has already been done in the past. So there's all sorts of things that we could have manipulated differently, which might provide even better accuracy. But unless we have more data, it's really hard to push the research further.
Right, that's the piece. So that kind of leads me to another question, kind of related to which I love, related to kind of how you're trying to get more folks kind of doing this. And I see in, I think, a few of your studies that, kind of at the end, you offer up all of your data and your sort of your algorithms and your codes and that sort of thing. Forgive me if I'm using the wrong terms. For others to use, kind of on these kind of open source kind of sites. What's that about?
Well, I try to share as much as I can. It came about because, and we'll probably discuss it later, I do research on the validity of single case designs. And what happens with the validity of single case designs is we often use simulated data or a few data that we extracted from the research literature. And then we compare different methods to analyze them. So this is the basic gist of it. So we simulate data, and then we ask either visual analysts to analyze them, or we analyze them using different statistical procedures. The problem right now in that area of research is it's extremely difficult to compare studies together because nobody was sharing their actual distribution of their data. So I'll give you an example. There are some studies that ask visual analysis to rate graphs, but I don't have access to these graphs afterwards to try a new method to see if they're doing better than visual analysts, even though the researcher already done all the work. They already have all these graphs. So in our latest study, which is not published yet, but which we submitted, I was really excited because what I did is I generated 1,024 graphs with different properties. And what I'm doing is I had 5 different experts rate the 1,024 graphs because it was essential to have behavioral analysis. I think it's better to have a few behavior analysts rating a lot of graphs rather than having a lot of behavior analysts rating a few graphs, because it's easier to see what properties of the graphs are throwing them off if you have them analyze 1,000 graphs instead of just 20. With 20, you'll be able to average, but then you get into the same issues that behavior analysts complain often about group methods. So we produce 1,024 graphs. We have the ratings for 5 behavior analysts. We have the results for different method of analysis, and we just put it for free on open source. And that one is on GitHub, which is a repository to share data, so that any researcher who wants to see what we've done, how visual analysts analyze graphs, can use our data, and so that we can have a comparison. So I hope that other researchers who develop new methods, instead of using their own graphs, will use these graphs so that we all use the same graphs to test the same models.
Yeah, that makes sense.
Because it's extremely difficult to compare from one study to another right now. It is feasible, but it's a challenge, and it's not always valid. And we've been seeing stuff that we weren't expecting because people haven't been sharing their data. And like I say, it's hard to get 1,024 raters to 5 raters to an expert BCBA-Ds to rate 1,000 graphs. Well, if others find a use for them, why not?
Yeah, yeah.
Because, I mean, that's really the future. And same thing for the algorithms. I mean, when we develop models, I want other people to be able to test them and compare them with theirs. Because the only way we're going to have the science progress is if people share.
Yeah, exactly. You can't be the only one doing this research.
And I mean, a lot of people are doing the research, but unfortunately, it happens more than my share of times when I ask people for their data and they won't share it with me.
Oh, interesting.
I mean, not always, obviously, but which is sad, because if we want to have the science progress, regardless of what science we're doing, if you share your data, you have others, and it's a standard in more and more fields anyways. I mean, it's a standard to share the actual data so that others can replicate. And we don't have as much of the reflex in behavior analysis, because we don't have clear ways to share it. So, for example, it would be so much easier if we had a repository, and we tried this a few years back, and we might restart the project eventually, where everybody could deposit their single case formatted in the same manner. Because right now, when you want to do studies of single case, you have to extract the graph, and then, yes, there's automated tools, but they're not that great, and they're still long. Like a graph still takes me a minute or two. If you want 1,000, you have like several hours of work to do.
Yeah.
Whereas if everybody would just deposit their data in an organized format within a repository, we wouldn't have that problem when we're trying to do meta-analyses, for example.
The third secret word is intelligence. Is that just like an issue of confidentiality, or of just folks just aren't aware that you can share your data?
Yeah, I think people are just unaware. I think people think that their data is confidential, but once you've published a graph, I don't want the name of the child. I just want the data points.
Yeah.
So we don't have an easy way to share single case graphs. That's one issue. People don't know how to do it. There's been an interesting recent paper about GitHub and perspectives in behavior science that tells you how to do it, which is one way. But people just don't think that it's important. They say, oh, well, it's just one or two. It's just a few participants. They can see it on the graph. That's fine. Actually, it would be super helpful if it was linked to a repository where you give me the specific percentages and where I can apply other methods rapidly, because it discourages the lack of sharing. And I'm not saying it's not intentional, but it discourages the use of data sets that already exist. So there's a ton of things that we would have loved to do with machine learning, but there's just not enough information in research articles. So we were unable to get the variables that we need. If that was all neatly in a repository, then I could just extract the data and do a replication,
For sure. So if there are researchers or folks out there that, maybe are listening and, are interested in sharing their data, how do they go about doing that? Like, is it a pretty simple process, or?
Yes. I mean, the simplest process to me is osf.io, which used to be called I don't know if it's called that, but Open Science Framework. So osf.io, or you can just put your Excel data there. I mean, as simple as that. It's
oh, interesting.
I mean, you could eventually, it would be interesting to have a standard format for single case designs. We're not there yet, but just that is very helpful. And I think people aren't sharing it too, because they think that sharing is for people who do code like me, because we're very used to sharing code. So, but sharing the data is also important, in my opinion, because if you want to replicate, you need the data. If you want to make sure there are no mistakes, you have to see the data. And, I feel like the number of, I regularly find errors in my own computations before submitting to a journal. So I wouldn't be surprised if there's a ton of errors out there, but because nobody's sharing the data, we don't know. And it's not a bad thing. It's normal. People make errors all the time. There are a lot of numbers. You flip a number, you make another error. It happens. I'm pretty sure it happens more often than we think. But without sharing the data, it's impossible to pick out these errors in the literature later on.
Sure.
Which is an issue with not sharing. And that's why I like sharing my code, because I say people, you can look at exactly what analysis I did, exactly the data. If you're not getting the same results, please tell me. Because we improve over time. It's not true. Like I was saying earlier, I'd be really surprised if we're using the same algorithms I'm using today in 10 years to make predictions in behavior analysis. I mean, people will find better ways to do it when they have bigger data sets. They'll use different parameters, which are just basically how the algorithm treat the data. So there's many ways to do it. But without sharing, it's extremely, extremely difficult to move forward because we're stuck. I mean, when we try to do some replications, we're stuck, or we're trying to use published data. It takes us forever to to extract the data from each study, and we can't replicate and test their hypotheses unless they share.
So you were saying, I just kind of caught briefly. You mentioned we don't really have a standard way of graphing.
Or it's a standard way. We have a standard way of graphing. We haven't had a standard way of sharing data from a single case design. So, for example,
I see.
Should I put the phases in a column and then the numbers, the percentage in the second column, or should I do it by row? If I do it by row and I change phase, but I make a tweak in it, how do I name it? If it's a combined design, how do I present the data? So we don't have a clear way. People put them in Excel or put them in GraphPad and graph them, but we don't have like a clear format where you would say like my data, all CSVs of single case data report this, a column with the phase number, the phase letter, for example, or a phase number, and then a column with the actual values.
Right.
And if there's more than one behavior, how do I report that? Do I do two separate files? Do I put them one side the other? So I see it myself when I generate graphs. How do I generate a multiple baseline graph? Do I use 3 different columns? Or do I put them all in one row? And then once the first, I'd say A1, B1, then A2, B2. I don't know. We don't have a standard. So I face that issue a lot because I do quite a lot of research on single case designs and I generate data, and there's no like accepted format of what it should look like when I put it in a simple, what we call a CSV file.
Yes.
So, I mean, I share my data, but people, even if everybody shares their data, there's still the challenge of nobody enters them in the same way. So I have to be able to extract them, but it's still faster than going into each article, obviously. And I still prefer data organized differently than having no data at all, obviously.
Absolutely. So this makes me wonder, gets me thinking about, I see a lot of alignment here. Have you thought about connecting with the precision teachers and the standard acceleration graphs that are all the same?
No, we haven't tried that, but definitely that would be interesting to see.
That would be interesting to reach out to someone like Rick Kubina or someone like that where all their research and all of the data that they put out is all on the same kind of graph.
Yeah, but the issue is not the graph, because the graphs it's how you save that data that's not in the graph, the issue right now.
Oh, I see. It's so how it goes in that comma separated value file.
That's the issue. Because most of the people do similar graphs. I can interpret just about any graph. The problem is how do people enter it in their Excel file, in the comma separated file, where they don't start all in the same column. So if I want to batch analyze them, it's a real pain. Whereas I always graph with the same template, for example. Right. So I can easily write a script that will take out all the baseline phase in like 10 seconds.
Yeah.
Whereas if people don't put in the same column, the same row, or they don't format it in the same way, it will not be able to be automated. So it's still, like I said, it's still easier than extracting data from graphs.
For sure. And that makes a lot of sense. And I could totally see everyone and their dog, filling in a table in a different way.
So that's a bit of the challenge for single case research. But we've been finding pretty cool, to go back to these study that we've been doing with single case research. I don't know how we got off topic, but
yeah, please, let's do that.
We're having a good chat, at least.
Yes. Let's get back to the machine learning for single case design study. Yes.
So what we tried to compare is to compare it to a gold standard, which is the conservative dual criterion method, which basically, or the dual criterion method, not even the conservative one, which uses the mean level and the trend to see whether there's a difference between baseline and treatment. And we compared the machine learning to it. And what we found is that machine learning was a lot more accurate. I'm going to take a few steps back. Okay?
Sure.
What's important when we're analyzing single case graphs is two things. Is we don't want too many false positives. So false positive is that you conclude that there's a functional relation in a graph, or there's a behavior change in a graph, when the behavior change you're observing is not occurring. It's just due to randomness, right? So that's a false positive, or a type 1 error rate.
Right.
Okay. The second thing is important is you want it to be able to detect most effects. So you want to reduce false negatives, which is called power, the proportion of which you are able to, the proportion of true positive that you are detecting.
Mm.
And that's something that's really important. It's called power. So you want to have low type 1 error rate. So basically, you don't want to conclude that a graph has a change when in reality it doesn't have one. And you want to have high power. That is, when a graph has a true change, you don't want your method to tell you that there's no change.
Right.
Okay?
Makes sense.
Yes, that makes sense. So these are the two things you're looking at. And surprisingly, we don't know that much about visual analysis and its validity. There are a few studies. There was one by Fisher that showed that it wasn't that great, Fisher et al. In 2003. But there aren't that many studies. What most of the studies have done in visual analysis is that they look at agreement between behavior analysts. So they look at whether all behavior analysts agree whether there's a change or not. But there's a fallacy within this reasoning, because two behavior analysts could agree, but still be wrong.
Right.
Unless you have a true value, you know the true value of the graph.
Mm-hmm.
And the only way to do it, to my knowledge, and if any listener knows another way to do it, please email me. But to my knowledge, the only way to do it is with simulated graphs, because then you can simulate a graph to have an effect and simulate to have no effect. Because if you're doing with a real graph, well, how do you know there's a real effect? Well, an expert told me there's a real effect. Okay, well, how do you know the expert is right? Well, maybe he backed it up with statistics. Yes, but statistics aren't perfect. So you're just going into circular reasoning in the end, because it's just like the chicken or the egg, and it's a bit of a challenge. So what we wanted to do first is look at the validity of the machine learning algorithm versus the DC method. So look at accuracy, power, and type 1 error. And what we found in simulated data is that machine learning has a lot more power. So we'll produce about the same number of type 1 error rates, which is good. But the advantage is that they can actually detect more effects that are true that the other methods are discarding. It really showed that when you compare the DC method to machine learning has an edge. This edge is around, I'm trying to look for my graph, its accuracy is about 5% better in general, right? On graphs with certain distributions. So now we said, well, for better or for worse, behavior analysts really love their visual analysis. But an issue with visual analysis is I can't even say for any given person what's their error rate. I don't know. So it's a bit odd for behavior analysts to be so attached to visual analysis when you don't even know the error rate that we're making, especially with our super reliance on inter-observer agreement. So we're strong in inter-observer agreement for behavioral measurement, but we won't want to use methods. So I feel that with the whole statistics things and structured methods to analyze data, behavior analysts have to throw out the baby with the bathwater, right? So of course, when applied for null hypothesis testing, and to groups, there are really huge issues to statistics or to structured methods. But it can actually be our allies when we're analyzing single case graphs. Mm-hmm. So then we did a new study, which is not published, and so it has not been peer reviewed. And I like to emphasize that because I'm a big believer in science, replication, and peer review. And what we found is that machine learning also outperformed BCBA-Ds trying to analyze graphs.
Wow.
So that was the 1,024 graphs I was telling you about earlier.
Yeah.
So we had 5 BCBA-Ds
BCBA-Ds, yep.
analyze 1,024 graphs. and none of them outperformed machine learning. And more concerning is their agreement isn't great. It's about 80% of the time.
Like even between the BCBA-Ds, you mean?
Yeah, I mean, between
Oh.
BCBA-Ds, it's actually the average is 73%,
Okay.
and some of them hit 80.
Okay.
But I mean, imagine if I told you, I'm going to diagnose you for cancer,
Yeah.
and 80% of the time my colleagues and I won't agree.
Yeah. Wow.
Would you trust that doctor?
Probably not.
No, but we still trust visual analysis.
Yeah.
And if you say, and I'll be totally honest, if you say in a paper that statistics should replace visual analysis, you'll get totally slapped. Believe me, I tried it by reviewers. Which to me surprises me because behavior analysts are such scientists and are all about we're natural science, we believe in. But when it comes to visual analysis, there's like this traditional or emotional attachment that is there for some reason.
Yeah, I hear what you're saying. Yeah.
It's like I say, it's like when we said no to stats, we threw out the baby with the bathwater instead of just saying, because it has evolved a lot. And there are some good stats that can be used even when you have dependent data. And that was an issue initially, and maybe when behavior analysis started, computers may not have been powerful enough to do what we're doing right now.
Yeah.
And it makes sense, or didn't have the tools. But nowadays we have tools. And what we found is that machine learning, when we look at the different expert, and that's what I like about this study, is that machine learning is the best at balancing between type 1 error rate and power. That is, my expert who has the most power, okay, more than 80%, has the worst type 1 error rate. He makes errors, or she makes errors almost 45% of the time.
Oh, that's so interesting.
Whereas the opposite, so that person has high power, that expert, but it has very poor type 1 error rate.
Yeah.
And we find the opposite is true.
Really?
People who have really low type 1 error rate, so make few mistakes, have really bad power because they're too stringent. So what behavior analysts struggle in doing is balancing this type 1 error rate with power, which makes total sense.
Yeah, 100%.
It's super difficult to do. How do you get adequate power while still controlling for type 1 error rate? And that's been the big challenge. And that's why we feel that the machine learning has been performing better than all these other methods, is that we can actually tell it the proportion. And that's what we did in this latest study that is in peer review. We actually told it, put more emphasis on type 1 error rate than power, because that's what we do in real life. Usually in research, we accept a power of 80%, but only type 1 error rates of 5%. So it's not the same type of error. So basically, we accept type 2 error rates of 20% versus 5%.
Okay.
So we could tell the machine learning algorithm, well, when you're doing that, make sure that you're putting more weight on the type 1 error rate. So it balances the power out to something that's reasonable. And our results are quite clear. I mean, 5 independent behavior analysts, BCBA-Ds, who are trained at different universities. So we were careful not to take people from the same lab.
Sure.
None of them could outperform, and none of them performed that greatly when you compare both type 1 error rate and power. And what we suspect of prior research, because there hasn't been that, and surprisingly, there hasn't been that much research that looks at the validity. Like I was telling you, there's a lot of agreement. Do behavior analysts agree between each other, but not are their conclusions actually valid?
Right.
And what we found is that, there are some visual analysis that are definitely better than others, but none of them offer a good balance between
the power and the type 1. Yeah.
And this is a big problem under certain characteristics of data. I couldn't tell you all off the top of my head, but one comes to mind is trend, which really caused issues.
Yep.
Most behavior analysts had poor power when there was no trend, which is a huge issue. We're asking behavior analysts to have stable data sets.
Yeah.
And they perform worst on data sets that had no trends for power. They made less type 1 error rate, but they were unable to have good power. And even with very large effects, this results persisted. So,
Right. Oh, wow.
so when we had an effect size, a standardized mean difference of 5, which is considered pretty large, the behavior analysts were a lot better, but maybe one of them achieved 80% out of the 5, even with an effect size of 5, which is huge. So, and whereas starting at about 3, the machine learning would have decent power, and 3 is probably towards the low end for effect size for single case design, or that's what we found in previous studies. So I don't know if I'm clear.
No, you totally are. You got me wondering though. Have you shared these results with those 5 BCBA-Ds?
Yes, some of them ask for them.
Yeah, and so
we shared them with them. We send them their file and the true values and the graphs, because we do open science anyways. You don't know who these experts are, and actually don't know either, because I try to stay removed so that it's really independent. But some of them specifically asked to have the true values so they could compare their true values with their ratings.
No, exactly. That's what I was wondering. And I mean, I'm wondering, did we hurt some self-esteems with this study?
I don't know. I mean, I wouldn't be surprised. I wasn't surprised by the results. I mean, given the studies on agreement, it's not surprising, because there are other issues in the ways that we use single case designs that we won't discuss today. But that makes total sense that we have even a small difference. We notice that even like a 10% difference or 20% difference in agreement, when you're applying this 10% error or 20% difference on multiple panels in the graphs, because now we're talking just about A/B graphs, but if you're applying to multiple panels and multiple baseline graphs, or if you're applying to multiple phase changes in a reversal graph, it just inflates it. So it's even, the problem may be worse than what we actually think.
Right.
Because I'm just doing A/B. So I'm not even, so this error is compounded on many phase changes or on many panels.
Okay. Yeah. Fair enough. Wow. Yeah. Because normally we wouldn't just do an A/B design, of course. So,
that's it.
Yeah.
So that's an issue. But unfortunately, our training in behavior analysis, and that's probably a personal critique of mine, is not very strong in stats. Like our basic training.
Right. Of course. Yeah. No.
Which makes that, people don't necessarily see it. We've ran into similar issues with multiple baseline designs where we're requiring a certain numbers of tiers to be significant. But if you do it statistically, you'll notice quite fast that if you require too many tiers to be significant, you'll have low power. So behavior analysts have been so obsessed with not making errors, type 1 errors, that I feel we're sometimes forgetting about power.
Yeah, absolutely. Yeah.
That's really what these studies have taught me. We're so obsessed with not making type 1 errors that we tend to
do that at the expense of the power. Yeah.
That's it. So do more false negatives, basically.
Yeah.
Which is not necessarily good for science.
No, that's not very helpful. No. So what are you working on now?
Now, right now, I'm working on some stuff on in the machine learning area. We're trying to see whether we can have better predictions of what discontinuous measurements to use to measure behavior.
Yeah.
So we're trying to figure out. It hasn't been that much of a success. I don't even know if it's feasible. Sometimes you start out with an idea and you realize that it doesn't work.
Yeah. Sure.
Trying to extract data from different treatments to try to predict treatment effectiveness based on a set of characteristics. So, for example, and Hagopian and colleagues have done a ton of studies on that, or many studies where they do a case series and then they report all their data in a table. So we've been trying to extract data like that to see whether we could use machine learning to predict whether an intervention would be effective with a child or not. We're trying now also to measure motor stereotypy on videos. So we've done vocal. So now we're seeing whether we could use videos to measure some motor. Now it has been done, but most of the time this research is not done by behavior analysts, or most of the time, nearly all the time. And what happens is that they do it like for 10-second clips, but it's really easy to do for 10-second clips. The hard part is to measure it during a 10-minute session and say what the percentage was. So that's what we're trying to do right now, expand and trying also to we have a new tutorial in the works, which we hope will get accepted eventually for behavior analysts to learn how to run these algorithms. So we wrote one on machine learning, but in that one, we wrote a whole tutorial for behavior analysts who know nothing about it, from how to download the programs to training a little model with different machine learning algorithms. So now we've done the same thing, but with a neural network, which are a type of machine learning algorithm. So it's a subtype, but a lot more complex. So we didn't have enough space in that other paper because it would have been like 80 pages long.
So that first one was like 45.
That's
so
it.
yeah.
So we split it, and what we showed in that study, or it's a tutorial, but at the same time we show something, is that machine learning also does better than visual analysis to analyze multiple baseline graphs.
So folks could follow these tutorials and sort of try to get similar results, and they don't have to go take a graduate course in software engineering?
That's exactly it. That's how and why they were written. So if you follow step by step, you shouldn't run into any issues. It's fairly straightforward. I mean, and they might not understand all the math because we did a matless introduction, but they'll understand how you can test a model on your own data.
And do you need like a special computer or special software?
No, because in behavior analysis, we don't have that many data sets that are that large. So, I mean, a basic computer, I mean, you don't want to do that on a tablet, obviously. But, I mean, if you use on a desktop computer, most of them should be able to run them unless it's really old. And the only issue I can find is if you're doing, like, with my single case research, I simulate data. So I can simulate, like, literally 1 million data sets.
Right.
So some of our studies have more than 1 million data sets, actually. So that's when it can get long if you don't have a good computer. But for the everyday use, and, for doing our tutorials, I don't think that it will be much of an issue. It's really when you're pushing the envelope with a lot more data that you need the power that comes in. And it tells you what programs to download and everything. Because, I wrote the tutorial like I would have liked somebody to teach me when I started. Because when I started, I was totally at a loss. I learned all about the math first. I had to write them from scratch with it was the way that they learned where I went to learn about it, which is okay. It's different. It's not like explicit teaching. Let's put it that way. But I learned. But I wanted people to have a painless approach to, like more an errorless approach to doing the thing. And obviously, we're very strong on open science, like I was saying. So, I mean, people email us with their questions or with their bugs, and we solve them at a distance within a day or two. I mean, that's not an issue. And we're preparing in the next
That's awesome.
6 months, probably, we're going to do another tutorial. We're going to do a online workshop on machine learning for behavior analysts.
Awesome.
So, or in the next 6 months, people don't know when this is going to air, but before or by June 2021, we hope to be doing another of these tutorial, because we did it last year. We had like 15 individuals participate. So it's just an introduction on how you applied these algorithms to data that I obviously share.
Very cool. Well, I think we'll have to make an effort to get this episode out a little before that to get folks a little bit of an intro, and maybe they'll be interested in the workshop. And I imagine there'll be some CEUs associated with that.
Yes.
And potentially, because I think there's a lot of folks who would find that super cool to be able to kind of try to do
we
some
call
of this
it,
stuff
we did it last year, 6 CEUs, like a 6-hour training. And it was really about machine learning or artificial intelligence for behavior analysis. And instead of talking about my research and conceptually what we did today, it's hands-on. So we load the data in Python in a program called Python. I show how it's organized. I show how you go get the algorithms and stuff.
And Python is something I've heard of it, but it's something you can download, or essentially.
Yeah, Python is basically a programming language that you can use across platforms. So that's why it's very popular. So whether you have a Mac, a PC, or a Linux,
right,
it doesn't really matter. Or I mean, Windows or Linux, it really doesn't matter. So it's easy to replicate, and it will function the same on all machines, which is the advantage of using it. And it's probably, arguably, the most popular platform for machine learning.
Fantastic! Wow, well, that's really cool. I think there's going to be a lot of folks out there, the budding, particularly some of our younger behavior analysts who are much more into the technology. I think are going to be keen to kind of tap into this and try this out, because there's A lot of cool stuff here. This is really kind of at the forefront of, I think a lot of potential to really change our field with this stuff to make things more accurate and make things more predictable. And yeah, I think this is just really amazing work you're doing, Mark. Really impressive. I kind of came into this interview a little afraid, a little nervous about my, sort of lack of knowledge of computers, but you've done a really good job of kind of describing this stuff in more layman's terms and throwing little bits of jargon in there for me to kind of get me on board. I think I might be interested in this workshop too.
Well, thank you. I mean, obviously, I know it's a challenge, and I know that the terms are probably what is the hardest. But I try to make analogies with behavior analysis as much as we can, because a lot of it is similar to what we're already doing with humans, but we're just teaching computers instead.
100%. Yeah. No, really cool stuff. I think this is probably a good place to leave it. We got some future prospects, some articles to watch for. We'll definitely have links to all the websites, the tutorials, the articles, and some of the other references. We'll mention Jordan Bailey's lab as well, and everything that you've sort of talked about in the show notes for folks. Really cool. I think this has really been one of the most interesting interviews I've done yet, particularly because it's just areas I had no idea about that was even happening, and so it's really neat to kind of see this kind of work happening. And I don't know if there's anything left you might want to share with folks that might
maybe a couple to finish. First of all, I just remembered that I told you there were 3 types of machine learning, and I didn't tell you type number 3. So for those who are interested, it's reinforcement learning, but it's not reinforcement like in behavior analysis. And it's really useful to solve problems, especially it's been used a lot with games, obviously. So if you have like different possible paths to a solution, for example, reinforcement learning is interesting, but just don't get once again thrown off by the term.
Gotcha.
It's not necessarily reinforcement like we do in behavior analysis, although there is a component of reinforcement in the sense that it can gain certain like amount of like points when it takes certain decisions with.
Mm-hmm.
So it's trying to optimize that. So but it's not necessarily like the matching law. Let's put it that way. And second thing, just to share to everybody, if anybody is interested in hearing more about it, don't hesitate to email me. I have an easy name to find, so just Google me, you'll find my email. I won't even say it here. It would be a pleasure to respond and have a discussion with you. Or if you're sitting on a huge load of data and you don't know what to do about it, I say it after every talk, give me a call or drop me an email. I will know what you do with your data. I mean, there are so many questions that we could do, and I work in an area where we don't have a university clinic. So I have to. I feel sometimes like I'm a guy. I do jump in these trash bins to try to find data.
You often have to outsource. Yeah, dumpster diving for data.
Exactly what I was looking for. I'm doing dumpster diving for data. So guys, if you have any data, don't hesitate to contact me. And it was a pleasure to be invited. So thanks for the invitation.
Thank you, Mark. So awesome. Thanks again.